Hi, my name is Nikhil Narkhede, and I am going to present a seminar on the topic which I have chosen, Fundamental Bound for Time Measurements and Minimum Uncertainty Laws. In this paper, I am going to present, the authors have tried to present a model which leads to fundamental minimum uncertainty in the determination of time. Fundamental theories of physics impose limitations on the accuracy of how we can determine physical quantities. This issue has been addressed by several authors over the years. For example, Salker and Wigner considered an idealized clock consisting of two mirrors with light bouncing between them, and they concluded that the minimum uncertainty of such a clock was proportional to the square root of the ratio of the time to be measured and the mass of the clock. We see such argument is based exclusively on quantum mechanics. Several authors have combined that argument with ingredients coming from gravity and reached the conclusion that clock's precision has a bound proportional to fractional power of the time to be measured. But there are some limitations. One cannot concentrate arbitrarily large amount of energy in a finite region as a black hole forms. In this paper, the author has presented an argument that only relies on the uncertainty principle, the time dilation in gravitational fields, and the basic error propagation theory. The existence of fundamental limitations in the measurement of physical quantities can have deep conceptual implications. For example, in the ordinary formulations of quantum mechanics, time is treated as a classical variable, which means that it can be measured with arbitrary precision, and other variables, on the other hand, are not treated this way, meaning that for every classical variable, there is a quantum operator present. The limitations in time measurement may lead to loss of unitarity in the formulation. This is because the variables measured by real clocks, as you see, cannot track the ideal classical uh, time assumed in the formulation of Schrodinger equation. From the perspective of time energy uncertainty relation, let us consider a microscopic quantum system playing the role of clock and a macroscopic observer uh, that interacts with the clock interchanging signals. Here we consider that observer is at a finite distance from the clock, and where Tc is the time measured by the clock locally, and T is the time measured by the observer who is at infinite distance from it. The time energy uncertainty relation is given by delta E into delta Tc greater than h cross by 2, where delta E Tc is same as the order of period of oscillations of the system. The clock does not necessarily have to be associated to a periodic motion. Also, it is a proposed extension that allows us to consider time as an observable even in case of non-periodic clocks. The gravitational time dilation was first described by Albert Einstein in 1907 as a consequence of special theory of relativity accelerated frame of reference. In general relativity, however, the gravitational time dilation is considered to be a difference in the passage of proper time at different positions as described by the metric tensor of spacetime. The relevance of this effect in determination of fundamental limitations to time measurement was emphasized by Frankel, and it is given by the expression given by equation 2, where t is time measured by observer at infinite distance, and Tc is the time measured by a clock locally. The expression 2 thus is T equal to Tc upon square root 1 minus Rs by R, where Rs is Schwarzschild radius of the clock and R is radius of the clock. From the definition of Schwarzschild radius from gravity, we have Rs equal to 4 GE by C square, C to the power 4, sorry, and E is energy of the clock. And usually G is the gravitational constant. For a standard atomic clock, this effect may seem negligible, but for an optimal clock, it would be important. the best clocks we can consider are quantum systems that are microscopic. This is because in such clocks, observer will not be able to go close to the clock, and its distance can still be considered as infinite. We can calculate the bound on time using the basic error propagation theory. The uncertainty in observed period of oscillation, we can calculate that using the method of propagation of errors, and taking the differentials for in equation 2, we get this expression or represented by equation 4, where we can see we get that expression in terms of 1 minus rs over r, and we also have delta r square in this expression. Now, from the definition of Schwarzschild radius in general relativity, we can replace this delta rs in equation rs square in equation 4 by considering the definition of Schwarzschild radius in general relativity, which is expressed by equation 5. And for the clock, that minimizes the uncertainty delta t using the uncertainty principle above, which we use to calculate delta rs equal to 4g square h square upon c to the power 8 delta tc whole square. Substituting equation 6 in equation 4, we get expression 7, where we see that delta Tc square appears both in numerator and denominator. So we can say that delta Tc is bounded, and also the size of clock cannot be smaller than its Schwarzschild radius. So 1 minus Rs by R is a positive quantity which is less than 1. Also, from equation 2, we can write the inequality. That is what we are doing here. We are using the fact that 1 minus Rs by R is positive quantity less than 1, and equation 2, from equation 2, substituting the value for t, we get this inequality 8, where we consider 1 minus Rs by R this as less than 1 positive. So we get this inequality 8. Assuming uh, R is radius of the clock here, and V is the mean speed of oscillations within the clock. So differentiating with respect to delta Tc, because we want to find the minimum value of time uncertainty, the minimum seems to be occurred at the expression given here by equation 9, and this expression is minimized when v is taken to be equal to speed of light, where we get the delta Tc equal to root 2 into pi power 1 by 3 t Planck square whole power 1 by 3, where t Planck is Planck's time. This corresponds to value of error propagation observed as we get this equation 11. We get this using this inequality 8. So we finally get delta t greater than root 3 pi to the power 1 by 3 t to the power 1 by 3 and t Planck to the power 2 by 3. So uh, we see that this bound depends on time t, and we can see that for time t equal to 1 second, this clock is 10 orders of magnitude smaller than the accuracy of some of the best current clocks in the world. Uh, and also we can notice that delta t over t, when delta t over t is small, larger is the time t measured, where time t is the time measured by an observer at infinite distance from the clock. And also we can observe that delta E over E can also be estimated for the interval of t equal to 1 second to be order of 10 to the power minus 20 using the uncertainty relation we have used initially. Summary of the presentation is using equation 2, it can be easily seen that this bound is saturated by a clock with a radius approximately given by r equal to 3 times the Schwarzschild radius. Previous authors got similar results, but they didn't assume any particular model of clock. They only considered the uncertainty principle and formula for time dilation in the gravitational field. So to summarize the presentation, I would finally say it is possible to obtain bound for the accuracy of reachable by a clock using only fundamental bounds of quantum mechanics and gravity, without even having to go into the details of practical implementations of the clock. So here are some references which I have used to study for this presentation. Thank you.